It's a pleasure to be here today. Thank you for inviting me to talk to you and to talk with you this afternoon. So I'm going to focus on talking about data that's collected as part of routine health care, specifically in the secondary healthcare setting and secondary healthcare records. And then I'm going to talk a little bit about the opportunity provided by participant or patient-generated data that's collected from outside of the system or the healthcare system by smartphones and wearable type devices. So I think we all know that the value of electronic health records is potential huge insights we gain from having access to the volume of data contained within the EHRs. And this includes data such as medical records, pharmacy data, labs, claims, radiology, etc. So a lot of information there and insights to be had for safety, comparative effectiveness research, and many other areas. So there's a big opportunity there, but I think there's acknowledgement of a fairly substantial challenge in using these types of data. It's often scattered across multiple systems in many different file formats, and these systems can be incredibly kind of burdensome for users to use. And this is just an example here of an advert where one of the hospitals advertising, a post was advertising that they had no EMR as a good thing because of what a burden that was perceived to be. And we can see that this example down at the bottom here, where I show these two plots, is from the clinical record interactive search system at South London and the Maudsley. And this is showing the different types of generated data over time from the inception of the electronic health record, and essentially showing that initially, a lot of information was gradually going into forms over time. And then there became a point where the system became, because of the forms being added, became too complex and too befuddling, I think. And at that point, the amount of information going into the forms declined, and that correlated negatively with the information that was being put into text, into the record system, just as narrative or other. And so basically users were bypassing the structured data entry once the EHR had become too difficult to use. So we have this challenge of in that there's a lot of data within the system which is in text, which we need to be able to handle. I don't think we're going to change, despite kind of the move to other systems, which are maybe slightly less burdensome. I don't think we're going to be moving away from there being text within an electronic health record anytime soon. And just at the bottom right here, I'm just showing within the electronic health record at South London and Maudsley, for something like an MMSE, which is which is supposed to be stored in a structured way, only 10% actually are. So that a huge amount are just being dumped into the free text. So we need to be able to think how we can handle text and unstructured data. It is easy for humans to input. Easy for humans to read, contained within many documents in a very different a variety of formats and agnostic to ontologies, and can capture non-health concepts. It's convenient for humans, but it's not convenient if we want to use it for downstream secondary use or other uses, in fact. And it's also problematic in the fact that it's kind of dirty and messy. We have spelling errors, typos, we have acronyms, negative terms, we have a challenge of disambiguation, we have things that relate to other people rather than the patient themselves. So working all of these things out is really challenging. And so, we need to be able to get a handle on this data for it to be cleaned, sorted, and arranged in order to take advantage of it. I guess the original way of doing this would be, and cleaning this data would be to have a human coding team sitting down and reading through doctors' notes, reading through paper notes initially. And then even though we kind of migrated towards electronic health records, those systems are still really still don't really resolve the problem. So the paper form is just migrated into electronic format, and we still have this issue of being able to process the data and requiring human coding teams to be able to do that. To be able to use this data in a kind of production capacity, though, we need to be able to process it and do that rapidly. So do that sorting and cleaning quickly. So how do we do this? Do we kind of scrap the infrastructure and the EHRs that we have, or do we develop new interoperable infrastructure and EHRs? How do we kind of address this? Well, the way that we've been thinking about this is to acknowledge that the health data is extremely heterogeneous, and adoption of healthcare interoperable open standards is uneven today at this particular time, and acknowledge that users will kind of bypass structured entry whenever there's a challenge with the UX, and recognize that natural language AI is required to make sense of this data. And so we've been working on a solution for a number of years called CogStack, which is an ecosystem of loosely coupled technologies. Its core principle is that it's open source, developed in partnership with the NHS, NHS trusts, clinicians, and domain experts, and is built around and supported by governance models that are replicated and localized according to need. And so, in short, it comprises a data component, firstly. So this enables real-time data ingestion and a query layer that's agnostic of the underlying EHR, which enables then a number of applications. And so that's kind of drawing in, aggregating and harmonizing data from many different sources and putting it into a common format, into a common bucket, if you like, which then provides the opportunity for building apps on top of that. And so it enables querying across millions of records in seconds. It's basically enables a kind of search engine type capability. Those searches can be saved as alerts. So, and as new data comes in near real time, it is ingested. Triggers those queries can trigger an alert, which can be in the form of an email, for example, and also enables visualizations and dashboards. So we've been using this to produce, essentially to understand what's trending in the record in near real time. So using this to provide kind of aggregation or aggregate keywords and phrases from the clinical data as it's being generated by clinicians. And we're using this particularly to produce a signal for secondary health planning. And so there are just two plots here from one from King's College Hospital and one from Guy's and St. Thomas's here, just showing kind of symptoms and then tests relating to COVID. So this is really giving us a handle on what was trending in the electronic health record relating to COVID symptoms. And it gave us a head start on the formal kind of tests coming back in the lab. So we had a few days warning, which enabled better planning because we were able to see what was trending in terms of symptoms. It also gave us a handle on new symptoms as they were beginning to kind of appear in the population. So loss of smell, for example, was appearing very early on in the record. So that's great. That gives us the opportunity to be able to access and search and produce dashboards, etc., and generate insights rapidly and in near real time. But we also have a requirement to create a better understanding, if you like, of the text beyond that. So beyond what is essentially kind of search. And so we want to be able to structure the electronic health record for downstream use. And so what we have for that is we have an NLP module, a natural language processing module within the ecosystem called MedCat, which comprises machine learning models to structure and organize this free text. And so if you think we might, it's analogous to kind of going from the free text through MedCat and output into an Excel sheet or similar, so structuring it for downstream analysis. So it's able to recognize concepts and synonyms for concepts, any concepts that are contained within a concept database, So typically we'll kind of annotate quite frequently with SNOMED, but it could be UMLS or OCPS, anything really, and that includes custom concepts. So the first step in generating these annotations from the record is unsupervised, in order to be able to do it at scale, and then we may further validate by experts and configure and do some additional kind of top-up tuning for specific models or specific areas. And these models are configurable and shareable. So we have this first step of just generating a base level annotation and then topping up with some supervised learning. So just a quick little kind of video here of how this works. So it's detecting, this is an app here. This is the kind of demo version, which is on the web, either at this link or this QR code here. So I must just got to point out that this is just not trained on any NHS data. So it's not particularly performant, the web demo, but you can give that a test. So it's able to handle things like spelling mistakes, and disambiguate. So, for example, understand whether HR relates to heart rate or whether it relates to hour, depending on the context in which the term's been used. And so you can see here that it's annotating with these SNOMED concepts. It's also annotating with additional meta annotations or annotations of annotations, such as negation, whether it relates to a current or past event or concept, whether it's relating to the patient or whether it relates to somebody else. And so just actually here is another example where I've just pasted in a little bit more text to this, and you can see kind of it's annotated with a bunch of SNOMED concepts, and something here it's labeled, generalized weakness as asthenia, and the code for that, the RCD code, whether the concept was positive and negative, for example, and this is confirmed as being affirmed. So that's there if you want to have a little play with that. But as I say, it's additional tuning may be required to target kind of specific and improve, to target kind of subspecialities and to generate kind of specific understanding of maybe specific kind of quirks or jargon or grammar. And so here we have just some plots where we've shown this in the paper, the learning kind of rate, the rate at which you kind of the model learns to detect the specific related concepts. And so the orange is where it's getting incorrect. And this is the number of documents along the x-axis. So as you can see, by about 60 documents where you've done some top-up supervised training, it's performing pretty well here. So it generally kind of learns with additional kind of a small amount of supervised training where the unsupervised bit of the model has not worked or hasn't worked so well. So these models are shareable and reusable between use cases, but also between hospitals. And as I say, the NLP improves over time. The more data it sees, the more types of data and spread of data, different ways that text is being used within hospitals, means that the model improves. So we did this, and more details of this are in the paper, but we trained the first model on a huge corpus of real-world data at King's College Hospital with James Tier there and team, and that was on over 17 million documents. And then we took this model and we trained it in, we tested it as it was, so kind of without any further training at UCLH and at South London and Maudsley, so a mental health hospital and then another large kind of physical health or general healthcare hospital. And we tested it without training and then with some additional top-up tuning. And we found that performance was pretty good with F1 over 0.9, 0.94, I think it was. So the models now have seen a breadth of text, both from mental and physical healthcare settings. And we have a model sharing agreement, which I think it is on the HDR Innovation Gateway. If not, it should be. that allows us to share these models with other sites that want to test the models and further tune them. So if you're interested in that, then do get in touch. And there's all code and tutorials are available at the links in the slides here. The other thing that's an important consideration was the ability to be able to de-identify the records and de-identify the text within them. So besides being able to detect medical concepts, we wanted to be able to detect personally identifiable information, and then to be able to replace or redact that. So the team comprising of people like Željko from within our group worked on this kind of PHI, personal information kind of ontology, to categorize the information. And then, you know, we kind of surveyed what was out there, and there weren't many tools that really kind of de-identify all of these kind of types. So most kind of, they only kind of identify or de-identify a limited set of the relevant information. So this AnonCat is similar to, as part of the kind of CogStack ecosystem, and is bird-based and trained across 3 hospitals currently. It performs well, but requires very kind of careful training, and certainly when it moves kind of from one hospital to another, it does need it needs some kind of further kind of specific training to that hospital. So here we kind of trained in GSTT, Guy's and St Thomas's, King's College Hospital, and UCLH. So yeah, we benchmark this AnonCat against things like Filter, and both require specific kind of top-up tuning to a particular environment. But Filter, you can see here that the performance, where performance less than 0.9 recall was marked in red, and AnonCat is doing quite a bit better. This is just being written up yet, and we haven't shared the models for this yet, but we will be able to do that as we kind of write it up. And of course, this gives us the opportunity to kind of review or view the whole hospital in terms of what's in it. And so this is just a preprint we put out a few days ago, which is a kind of descriptive view of all the data collected within King's College Hospital from over 1 million patients over a period of, like, it was about 10 years or so. And you know, we annotated there was 157 million SNOMED annotations for over 1 million patients there. And just on the left, just some initial kind of view of this, looking at a kind of age of onset of age of first detection of a number of disorders within the record. And then on the right here is just showing how we then created some embeddings from the for each patient, and based on the SNOMED disorder codes, and then clustering those to look at how kind of the patients are clustering together according to their pattern of, according to their code SNOMED embeddings. And there's a link here to GitHub with some more of the visualizations there, and then obviously there's the preprint there, and then a description of the data set itself and the resource as a whole on the gateway. So of course we need to be able to, once we have the annotations, we need to be able to store them, to be able to do something with them smartly. And so on the previous slide was just a survey of kind of what we have there, but we need to be able to kind of more intelligently query the data, I guess. And so we need to be able to make the annotations useful to clinicians and other researchers. And so we can move the concepts into a database that will allow anybody to be able to query and utilize the annotations. So a graph database is particularly kind of suited for a number of reasons, not least because the UMLS or SNOMED ontology can be imported in as well, so that it enables a kind of queries such as the ones here at the bottom, where we kind of want to look at all patients that might have dementia or of the disease that's a direct child of the concept dementia, for example. And so there's a tutorial on towards data science here. If you just Google that, you'll come across that if you want to kind of have a look at that in a bit more detail. Just the figure here is just showing diseases, symptoms, medications and procedures associated with the patients in blue, and my documents in pink. Okay. And so, you know, this has kind of enabled rapid early insights, the ability to kind of characterize the record and structure it in this way. So we were publishing early preprints with regular preprint updates as numbers increased during the pandemic. And these final publications were much later. The preprints were much earlier, with the code shared on GitHub for multi-hospital kind of replication and validation. And so these kind of analyses, though, were something, you know, detecting something specific or predicting something specific and using a specific set of inputs in order to be able to do that. So we wanted to think a little bit about what the opportunity was for generating some more kind of general models, and thinking about the kind of the resource as a whole, and particularly take advantage of some of the advances in kind of large language modeling type approaches. So here Željko adapted a GPT, generative pre-trained transformer, GPT version 3, to learn what future medical problems a patient might expect. So not predicting, say, hypertension, but predicting what, you know, anything in terms of a future event. And the first thing was to look at whether we could predict the next thing, and the next thing to do after that was to see whether we could kind of simulate the future. So predict one thing and then predict the next thing, and then the next thing, and then the next. And we were specifically kind of focused on diagnoses or risk of disorders, on symptoms, what symptoms might appear, on what medications people might take, or what procedures might be given to patients. And so in order to do this, what we were doing was basically pulling the data from the EHR, as I kind of described, and then taking all of the documents for the patient, and then generating the annotations for those, and then kind of structuring and ordering the annotations as input for Foresight, essentially, which then kind of using the kind of GPT type approach models the ordering of these patients. So it's essentially putting in, rather than putting in text, we're putting in the processed MedCat annotations. We trained at King's College Hospital and at South London and Maudsley, and also on the MIMIC US data set. And then, you know, so we put these concepts into 192,000 concepts were included. And in the groups that I mentioned, the concept types that I mentioned, and we created buckets, and then we did some filtering of these concepts within the buckets and structured them a little bit, binned them a bit. And so in terms of predicting next concept, we were able to detect the next concept. This is kind of looking at King's College Hospital and SLAM patients. So SLAM had a much smaller data set, but it was trained on a much more narrow kind of cohort of patients, because it was only trained on those with serious mental illness. Whereas King's College Hospital was much larger, but it was much broader in terms of scope. And so here, what we're trying to do is try to predict the top one, or the top 5, or make a prediction that's within the top 5, essentially. So our top 1, we want to match exactly the next concept. If we predict a concept and look at the top 5 predictions, is the true concept in the top 5 predictions? And then for the top 10, we're predicting the top 10 concepts and checking to see whether the true concept is within the top 10. And so we did, you know, we're doing okay here at top 1, I think top 5 and top 10, slightly better on SLAM, but that's because It's slightly narrower, as I said, in terms of the broader scope of patients. But if we're predicting a concept in the top 10, do very well. But bear in mind that this is 192,000 concepts that we're predicting from. So predicting maybe at kind of 0.7 or 0.8 is not too bad in terms of precision when you bear in mind that it's a real kind of high number of classes. And then we took some manually created 34 fake patients and used Foresight to predict the next top 5 next concepts for each patient. And then we had clinicians validate the top 5 predictions for relevancy. And the top prediction was relevant in 97% of the cases, and 88% of the top 5 predictions were relevant. So the focus here is really on precision. And if a patient has a disorder, it's very likely to be, so basically if a patient has a disorder, it's very likely to be mentioned multiple times. So missing 1 or 2 of them isn't particularly important. And so it has potentially has a number of utility and in a number of areas, I think. I think the key thing is to note the limitations. So it can only predict concepts seen in the training data, obviously. It cannot, we've got this challenge of accurately estimating time, which is difficult to do. And of course, it learns biases in the data, so it's being trained on a hospital. So if a hospital, there's certain practice within the hospital, it'll learn that practice. But that gives us opportunities to kind of test the modeling or learn from the model what the practices are within a particular hospital. And so just we have a little web app for this, which I'll just show here. So this is quite basic at the moment, but essentially it allows you to construct a timeline. Here I'm only displaying King's College Hospital trained model. But if I put it, you have to start off with ethnicity, sex, and age. So if I want to start off with, say, male, if I put myself in here, and then put this in. And then, I want to predict, say I want to predict disorders. What would be the most expected disorder for me, according to King's College Hospital? You can see that hypertensive disorder is predicted first, then, a range of disorders in order of kind of probability. If I click on saliency, it'll tell me why or which variables that have been put into the timeline are making the biggest contribution to the prediction. So why it's made a prediction based on things. So you can see here that 50 is the major contributing factor to that. If I say that I'm younger than I am, then rerun again. It will suggest a different set of disorders for me with a different probability. Pretty simplistic. If we take, say, an example here, another pre-constructed, so one I rolled earlier here was another timeline. So these timelines, a bunch of concepts together, separated by age, for this ordered timeline of events or concepts that have been mined from the record. And then say we want to get disorders again. A prediction is made of sleep apnea with a saliency here. It's assigning different weights to each of the input variables, and that changes according to which disorder we think we have. Also, you are able to consider, rather than creating a structured timeline, you're able to go one step back and just put in some raw text description and make a prediction similarly. So that's just it's more a kind of tool, I guess, that we're playing with at the moment, rather than anything serious, and we're testing what the model does and the weak points of the model, etc. So of course, we really want to kind of think about how we kind of just operationalize NLP a little bit more and some of these things. So this is an example here where we've drawn from structured and unstructured sources and used NLP to enable some clinician-facing tools for caseload and population health management, for patient-level disorder-specific dashboards, and with providing kind of links through back to the EHR, so that you're kind of able to navigate out of the EHR to this and then back into it. So this is being used in various ways, ranging from care delivery and planning from frontline clinicians. It's enabling medication reviews from the pharmacy teams, and resource allocation or reallocation by management team. So the automatic medication reviews for pharmacy teams are a lot more accurate and offer huge time savings. We're trying to kind of quantify that a little bit at the moment, but it definitely improves things. So that's kind of one of the ways in which we're kind of trying to take this back to the bedside, I guess. And just some evidence here of how this has helped. So this is an example where we're generating a summary, like on the previous slide, of measures that physical health kind of measures or care interventions that are being undertaken within a mental health care setting. We're seeing prior to this kind of dashboarding being in place, and then post. So these plots are showing the improvements in the management of caseload and patients' physical health. So this was basically a team of 6 people from the physical health team, managing a caseload of 33,000 patients and managing to get this kind of uptick through having better access to data. Okay, so just to highlight that, you know, critical to all of the work that we're doing is making sure that we do it in partnership with multiple stakeholder types, and we're clearly kind of trying to address the priorities of patients. And so all of the work has patient oversight and engagement at all stages, from project initiation through development and kind of result stages. And this is just a piece of work we're doing here with parts of the HDR text analytics program, where we've been working to get the views of clinicians, IG leads, researchers, and patients, and the public, on creating an NHS free text data bank to help streamline access to data for further method development, and kind of reducing our dependence on things such as Mimic in the US. Okay. And so just on this kind of section, finally, I just wanted to summarize and end that I guess these kind of approaches are enabling a bunch of kind of downstream use cases and can enable sharing and integration with things like ICSs, you know, and key, I think, to getting timely extractions of data and structuring those data for further onward use. And if this is kind of area that you're interested in, then you'd be very welcome to join the community online at the discourse link there. But also, if you want to kind of talk about kind of implementing or standing up or collaborating in some of this, standing up some of this, and or collaborating more generally, then please do feel free to drop an email to the email address there, or to myself. And the GitHub link is there for some of this work. Okay, so just moving on to the next section, I just want to switch a little bit to talk about the opportunity around patient-generated data from mobile devices, that being smartphones and wearables. We know that most people, you know, are carrying these devices with them pretty much 24/7. So I want to think about the opportunity there. And it's really, you know, there is these devices, I think, help us give us the potential to shift from the current paradigm of kind of sparse, intermittent and subjective kind of reporting during periods of sickness, shifted to kind of the opportunity for a more continuous, kind of pervasive and passive and objective monitoring or throughout the disease continuum. So, you know, bearing with what is available nowadays in terms of the technology, you know, and the sensors, a wide range of parameters can be measured. And some examples are shown here, covering domains, behavioral domains, physiological domains, environmental domains, for example. And a curated list of endpoints is maintained, is in the link here and maintained by the Dyme Society. And so can we kind of use these data streams to kind of infer mental or physical state from a kind of derived digital phenotype? So this was the aim of a major depression study that was part of the European IMI Radar CNS program. This was a 5-year project focusing on potential for remote monitoring of MS, epilepsy, and depression. And so a key thing here was we needed to be able to develop a platform at the start of this project to be able to collect data. This was in 2017, I think. To be able to collect data that has the capacity to handle, to be able to handle data with volume and velocity and variety, and make this data kind of available to multiple types of consumers in the way of feedback or intervention or clinical dashboards and research data sets and APIs. So there was very kind of limited kind of capability for this within the kind of community generally, I think, and some systems kind of exist with covering kind of some of the components, but many have a kind of proprietary element to them, or not kind of quite covering all of the requirements. And so we developed a platform called Radar Base as a fully kind of open source platform released as an Apache 2 under Apache 2 license. And you can take Radar Base and deploy it wherever you want, either on cloud or local premise. You know, and the thing about it is it's kind of scalable and extendable, so you can kind of integrate new devices or customize it to your kind of requirements. So as I say, it's open source and modular, extensible, and allows real-time data streaming. And it's broadly kind of comprised of, or broken down into a number of components. There's a kind of passive remote monitoring component, which relates to sensors. And that broadly comprises of 3 domains. So that's wearable devices and phone sensors, or passive remote monitoring app that integrates wearable devices and phone sensors. It's third-party kind of RESTful API integrations, and IoT, Internet of Things, sensor integrations. And then there's active monitoring. And so active remote monitoring tasks, these are kind of cognitive tasks or questionnaires or speech tasks. And these are kind of measures that can be configured or tailored according to the study and according to a protocol, or, you know, specific timings that you might want those. And then there's kind of back-end infrastructure, and this provides kind of data analysis capacity and storage and management, UIs and project management, along with visualization, data storage and analysis. Okay, so just another slightly more detailed view of the platform there, which I'll kind of skip over a little bit. The active app has capability to you know, to easily set up and enroll people, planning according to when you might want notifications we sent to people regarding kind of questionnaires and whatnot, the questions themselves, task calendars, and various other kind of settings. So highly configurable. The devices integrated into the platform, some of those are described here, and with more being added by the community as we go. And it's currently being adopted in a kind of wide range of different ways. So more than 45 case studies, around 20 kind of disease areas, with around 13 devices and apps integrated into the platform. And so this is a kind of best guess, because I don't really know how much it's being used, but I guess these are just based on the studies that we know about. A critical thing is to be able to generate digital markers or biomarkers from the sensors. So it's kind of transition from low-level sensors through to high-level kind of digital markers, and then subsequently disease or disorder insights. So in this example here, I'm just showing a kind of visual kind of representation of the kinds of things that are relevant to the major depression study that we were doing. And so a critical thing is trying to standardize this in some way, standardize the generation of these kind of digital phenotypes, digital measures from underlying sensors from different devices. So trying to, I guess, standardize those such that we can generate reusable or code to encourage reusable definitions and generation of these kind of phenotypes. So just in following on the theme of depression, we've been using or deriving various phenotypes for mobility, quantifying home stay, for example, or moving time, or moving distance, the number of clusters that a particular person will be in. So this is using GPS, but not their exact location. It's kind of obfuscated location data, but we can still work out kind of based on the time that somebody's at a particular place, and whether it's a cluster as to, whether it might be a home setting or whatnot. But it enables kind of create nicely, slightly, decently enough grained information about mobility and things like that. And then combined with Bluetooth connectivity from devices, get a picture for the sociability, and also using the device to generate metrics of gait, and also sleep and speech as well. So speech either by a task, a free speech task, or speaking from a script, and speech was, we're generating. It's a really interesting and exciting area, and I think a real kind of focus for the future for us for remote monitoring, and generating a range of different speech parameters across speech timing, prosodic features, phonation, articulation type features. And I think we have the largest longitudinal speech data set in depression. And so this is, if people want to collaborate on this data set, or these data sets, then please do get in touch. We've only kind of scratched the surface, I think, of what's the potential for some of this data. And, a critical factor, though, in all of the kind of mobile health studies is to understand engagement, and to address and improve engagement. Engagement is a challenge for these studies, and how people engage with them, and factors that drive the engagement are really need to be understood. So this is an engagement within the depression component, again, of this radar CNS program. And here we wanted to understand, firstly, whether different types of engagement, according to, whether it was questionnaire data, or whether it was data from the Fitbit device, or whether it was a sensor data from the phone. So whether it was active or passive, whether that affected engagement. And you can see that, we can see that passive data was more easy to collect over time than say active data. We had a drop off in phone passive data, probably because it was quite a burden on the phone initially, in terms of the sensors that we were collecting data from. It meant that the battery went down quite quickly. So, but overall, it's easier to collect. It seems to be easier to collect data longitudinally from if you're collecting it passively than actively. Other things we understood from this were that the least engaged group had the highest depression severity, symptom severity at baseline. So that's a real kind of, as you might expect, really, but it highlights the need to target these kind of things quite specifically, possibly to certain groups of participants. Younger age people, males and those with higher number of comorbidities were more likely to disengage. And we were also kind of quantifying things like how long it took people to respond, the way that people were using the phone and completing surveys. And so the least engaged group took longer to respond to notifications, longer to complete surveys. So, this is an area that requires further research to understand the kind of socio-technical and human factors for digital mental health tools to engage them in these kind of projects. So I just wanted to highlight here, this was during the pandemic, we were able to kind of use these existing cohorts to generate rapid insights into the impact of things like the non-pharmaceutical interventions, such as lockdown. We're able to do this across multiple countries. So looking at, collecting these metrics and to get a picture of how well or how much people were complying with these things like lockdowns in terms of home stay, the distance people were traveling, the numbers of steps, their kind of their sleep, and the various activity and time people were going to bed, etc. And so really get an understanding for what people were doing through more kind of passive means. So very kind of complementary to things like symptom trackers such as Zoe. These were we were looking at the passive data that was coming in from existing cohorts. And this led us on to look at going into COVID a little bit more and using Radar-based platform and an app we created called MassSci, which sits on Radar-base, to initiate a project called COVID CoLab, which was to understand and investigate COVID and long COVID using Fitbit devices, and then the phone data and survey responses. So this was done in collaboration with Fitbit. It stood up kind of in a few weeks, and Fitbit advertised it within the app and within their app, and we managed to get 17,500 people register and sign up to this, and 1,700 of those had or received a positive diagnosis of COVID at some point. So this was kind of quite nice in that it was a citizen science study, that we were able to stand up very quickly and get high numbers of people involved. And a key point here, I think, is that because we were just taking people who had existing Fitbits and they were allowing us to access their data, we were able to get not just the data from the point that they enrolled in the study, but we were able to retrospectively collect the data, in some cases going back many years, so able to generate this kind of fantastic baseline for individuals. And then I guess the key finding here was we just put this preprint out yesterday if you want to go and have a look at some more detail on this, but resting heart rate was something that remained elevated post onset of COVID. And so that subsequently kind of led on to another study again around COVID, focusing on convalescence. So we just took that app and took the platform and using it in this NIHR convalescence study with Nish Chaturvedi and at UCL. And so characterizing symptoms of long COVID, risk factors and duration. And so we flipped this time from a Fitbit to a Garmin VivoActive 4 device to capture exercise and capacity and heart rate, respiration, and then to complete regular online questionnaires and tests on cognition integrated with Cognitron. And then there are in-clinic assessments for imaging and various other kind of data being collected on these individuals as well. And then we're taking that further actually in putting the remote monitoring onto NHSD with Nish as well. So augmenting existing kind of long cohorts with wearable capture. So I just wanted to highlight just one further study here. This is a lung study, which is a respiratory disorder study, which is going on at, we're recruiting patients through UCLH. And it's in partnership with the Maudsley BRC as well. The critical thing here, though, to point out is that with this one, we're focusing on generating, collecting data and detecting exacerbations in function, but then in real time kind of making a prediction, and then on that prediction sending an alert to participants for an exacerbation, asking them to complete an exacerbation rating scale. So we're requiring responses at the time of the model making a prediction, collecting those responses, and then iteratively kind of improving the model based on what the real-time kind of labeling that participants are doing. So just to finish off here, this is a platform that's available for all. The key thing is that we're operating a mobile health as a service type model for radar-based, or starting to. If you're interested in kind of standing up a project, then and you don't, the code is obviously all open source, so take that and stand up. But if you want to kind of collaborate or want to have a project hosted as a service almost, then get in touch. And that includes either with or separately to that, if we have a kind of growing number of templates for protocols, data management plans, ethics applications, etc., for mobile health type studies, if you'd like to get some help with that as well. And so it's a very large kind of or growing community now around that platform, over 200 Slack users, and the platform has a kind of life of its own, if you like, with a multinational kind of collaborative team. Tech partners includes these, and we're a kind of key next step for us is to working with Kathy Sudlow and others, including Tim Chico, on how we try to kind of establish a linkage with NHS data, or routinely collected data. And the first challenge there is thinking about harvesting and consenting to look up NHS IDs and then do linkage based on those. So, but we're just evaluating how we'd do that, and then to what, getting the consent, and then to what extent people would be happy to donate those IDs or to enable the linkage. And here, just finishing off now, just acknowledge all friends and collaborators and teammates here in the slide across King's, across UCL, across and UCLH, across South London and Maudsley, Guy's, King's College Hospital, and there are many others as well. And this is just recognizing some of the kind of institutions and groups. And thank you finally to all patients, participants, and carers. So I'll leave it there.
That was great. Thank you so much, Richard. There are a few questions in the chat, but if anybody wants to speak, please raise your hand. So Robert asked, how easy is it to add to the recognizable dictionary of MedCat, taking into account local colloquialisms and abbreviation?
Yeah, it depends what it is, obviously, but adding a concept to the concept database is easy. It's the standard process for that. Whether it then performs well is obviously depends on what it is. It depends how many instances of it. But you saw in the plot where I showed the kind of blue and orange, there's generally typically quite a quick learning rate for new concepts or new terms, non-standard kind of things that are wouldn't be in the concept database.
Okay, thanks. Syed asked, would the order of variable selection matter, or does it matches up and all records with the selected characteristics?
Is that? Do you mean in the? Do you mean in the kind of foresight stuff? The order does matter because it's ordered. I mean, if you have stuff in buckets, so you can kind of have a separator which separates a group of terms by some time, and then
Darren is saying in the concept predictor.
In the concept predictor, yeah. So within a bucket, the order doesn't matter, as far as I'm aware. But between buckets, it does matter. Yeah. So the whole idea is that you have things separated in time, and the order of those would matter. Because I mean, well, depending on the use case, but typically you want to order things, and you're using the ordering in which they've occurred as an important component of it.
Thanks, Richard. Lana asked, how difficult or easy is it to obtain ethics approval with NLP study, as free text may contain some patient identifiers?
Yeah, so this, I mean, de-identification is obviously a challenge, and I think we're not talking about de-identifying data which is then kind of shared openly. We're talking about de-identifying data which is then stored in or kept in a TRE, or in a trusted research environment or other safe kind of a setting. So it's typically okay to there's an acknowledgement that the de-identification won't work perfectly, but the data is staying within a safe environment. So it is possible to get ethics to do that. And so there are models such as the CRIS model of governance down at the Maudsley, and there's one Kerry and at King's and Jerry at Guy's, which now has an overarching kind of governance ethics in place to allow any project with local oversight to use text within their kind of environment. So there are kind of governance docs that could be, or governance components that could be shared. Yeah.
That's great.
So, but yeah, so I mean, it's a kind of with the free text data bank kind of initiative. The idea would be that we created a resource that would be more open, because even though we're de-identifying but keeping in a TRE, it's still kind of difficult to get access to these data sets.
Richard, your timing was perfect. Thank you so much. The presentation was great, and thanks everybody for joining.